Take a look around you. Everything you see, everything you can touch, is made of matter. The chair you're sitting on, the screen you're reading this on, even you, this is the stuff we know. It's made of atoms, protons, neutrons, and electrons. For a very long time, we thought this was it. We believed the entire universe was made of this ordinary, visible matter. We thought we had a pretty good handle on what the cosmos was made of. But we were wrong. In fact, we were spectacularly wrong. It turns out, all the stars, all the planets, all the galaxies, and everything in between makes up less than 5% of the entire universe. So, what about the other 95%? That is the biggest question in physics today. It's a cosmic secret hiding in plain sight. This missing stuff doesn't shine. It doesn't reflect light. It doesn't seem to interact with our world in any way we can directly see. We call it the dark universe, not because it's evil, but because it's invisible to our telescopes and instruments. Imagine trying to understand the ocean by only studying the foam on top of the waves. That's our situation with the universe. We are just beginning to peek beneath the surface. If the entire universe were a giant library, we've only read the table of contents. The vast majority of the books are written in an ink we can't see. We know the books are there because we can feel their weight on the shelves. We can see the shelves groaning under the load. But we cannot read the pages. The mystery of the 95% is actually two separate puzzles rolled into one. Scientists have given names to these two invisible components, dark matter and dark energy. They might sound similar, but they appear to do completely opposite things. On one side, we have dark matter. It's the universe's hidden scaffolding. It clumps together, creating immense gravitational fields that hold galaxies together. Without dark matter, galaxies would simply fly apart. Think of a spinning merry-go-round. The kids on the outer edge have to hold on tight or they'll be flung off. In a galaxy, the stars on the outer edge are moving way too fast. The gravity from the visible matter isn't nearly strong enough to hold them in their orbits. There must be something else there, something massive and invisible, providing the extra gravitational grip. That something else is what we call dark matter. It's like the invisible glue of the cosmos, binding everything together. On the other side of this cosmic battle is dark energy. If dark matter is the glue, dark energy is the force pushing everything apart. And it's winning. In the late 1990s, astronomers made a shocking discovery. They found that the expansion of the universe isn't slowing down, as everyone expected. It's actually speeding up. Having two enormous separate mysteries is not a situation that scientists enjoy. Physics loves simplicity. It loves elegance. The history of science is filled with moments of unification, where two seemingly different phenomena were revealed to be two sides of the same coin. For example, electricity and magnetism were once thought to be separate forces. Then, James Clerk Maxwell showed they were both parts of a single force, electromagnetism. This was a revolutionary breakthrough. It simplified our understanding of the world and led to technologies like radio and electricity generation. Many physicists wonder if a similar breakthrough is waiting for us now. Could dark matter and dark energy be connected? Is it possible they are not two separate things but different manifestations of a single underlying entity? This is the central idea behind a fascinating and speculative concept called dark fluid. The theory proposes that a single exotic fluid fills the universe. This fluid would behave differently depending on its surroundings. In some places, like within and around galaxies where matter is dense, it would act like dark matter. But in the vast, empty voids of space where matter is sparse, this same fluid would behave differently. So, let's start with the first piece of this puzzle. Dark matter. How did we even figure out that something invisible was out there? The story begins with a Swiss astronomer named Fritz Zwicky back in the 1930s. He was studying a huge cluster of galaxies called the Coma Cluster. It's a cosmic metropolis, packed with over 1,000 galaxies all swirling around each other. Zwicky did something clever. He measured how fast these galaxies were moving, and what he found was completely baffling. The galaxies were moving at incredible speeds, far too fast to be held together by the gravity of the stars and gas he could see. The idea got a major boost in the 1970s thanks to the work of an American astronomer named Vera Rubin. She wasn't looking at galaxy clusters. but at individual spiral galaxies, much like our own Milky Way. She was measuring how fast stars orbit the center of their galaxy. Now think about our solar system. The planets closer to the sun, like Mercury, move very fast. The planets farther out, like Neptune, move much more slowly. Everyone expected to see the same thing in galaxies. But that is not what Vera Rubin found. At all. She discovered that the stars on the outer edges of galaxies were moving just as fast as the stars closer to the center. If you can't see something and you can't touch it, how can you be so sure it's there? Besides the speed of stars and galaxies, there is another powerful piece of evidence for dark matter, and it comes from Albert Einstein. Einstein's theory of general relativity tells us that massive objects warp the fabric of space-time. This effect is called gravitational lensing. The massive object acts like a cosmic magnifying glass, bending and distorting the light from the object behind it. By measuring how much the light is bent, we can calculate the mass of the object doing the lensing. One of the most famous examples is the Bullet Cluster. This is actually two galaxy clusters that have passed through each other. When they collided, the hot gas from each cluster smashed into itself and slowed down, creating a shockwave. But the dark matter, being a ghost, seems to have passed right through the collision without slowing down at all. Using gravitational lensing, astronomers mapped the mass in the cluster. They found that most of the mass is not where the visible gas is. Instead, it's located in two separate clumps that have moved ahead of the gas, right where the dark matter should be. Now we turn to the second, even bigger piece of the cosmic puzzle, dark energy. The story of its discovery is a tale of scientific surprise. To settle the debate about the universe's fate, two independent teams of astronomers set out in the 1990s to measure the slowdown. They would use a special kind of exploding star called a Type Ia supernova as a standard candle. Everyone expected to find that the expansion was slowing down. But science is full of surprises. When both teams analyzed their data, they found something completely unbelievable. The distant supernovae were even dimmer than they were supposed to be. The only way for that to be true was if the expansion of the universe wasn't slowing down at all. It was speeding up. Imagine throwing a ball up into the air, and instead of it slowing down and falling back, it suddenly shoots upwards, faster and faster into the sky. That's how shocking this discovery was. This finding turned cosmology on its head. It was so revolutionary that the leaders of the two teams were awarded the Nobel Prize in Physics in 2011. There had to be some kind of energy inherent in the fabric of space itself, a repulsive force that was pushing everything apart. So, what is this dark energy? The simplest idea, and the one that fits our observations best so far, is something Albert Einstein himself proposed and later discarded. He called it the cosmological constant. Back in 1917, Einstein was developing his theory of general relativity. At the time, everyone believed the universe was static, so Einstein added a fudge factor to his equations to make it stable. When Edwin Hubble later discovered the universe was, in fact, expanding, Einstein famously called the cosmological constant his biggest blunder. But fast forward 80 years, and the discovery of accelerated expansion brought it roaring back. Perhaps Einstein was right for the wrong reasons. Let's try an analogy to make this clearer. Imagine you're baking a loaf of raisin bread. The dough is the fabric of space, and the raisins are the galaxies. Now imagine this isn't normal dough. Imagine this dough has a magical property. The more it expands, the more dough is created in between the raisins. This new dough also expands, creating even more dough. The raisins wouldn't just move apart, they would move apart at an ever-increasing speed. So, we have two enormous cosmic mysteries. Dark matter, the invisible scaffolding that pulls galaxies together, and dark energy, the mysterious force that pushes the entire universe apart. For years, scientists have treated them as two separate problems to be solved. But what if that's the wrong approach? What if these two seemingly opposite phenomena are not separate at all? This is where a truly fascinating idea comes into play, the theory of dark fluid. Think about water for a moment. Water can exist as solid ice, liquid water, or gaseous steam. It is all the same substance, H2O, but it behaves in dramatically different ways. The dark fluid theory suggests something similar for the dark universe. The same underlying fluid could, in a sense, change its state. It could freeze into a clumpy, gravity-attracting substance, where matter is dense, and evaporate into an expanding, space-pushing substance in the vast emptiness between galaxies. This chameleon-like nature is what makes the theory so compelling. It could solve problems that the separate theories struggle with. To get a bit more specific, some physicists have proposed that this dark fluid could be a type of quantum phenomenon known as a Bose-Einstein condensate, or BEC. This is a state of matter that occurs at incredibly low temperatures, where particles essentially merge into a single, collective quantum state. They stop behaving like individual particles and start acting as one single entity, a superfluid. What if the entire universe is, in some sense, a giant superfluid? In this version of the dark fluid theory, the universe is filled with extremely light hypothetical particles. In the dense environment of a galaxy, these particles would condense and form a superfluid that clumps together under gravity. But here is where it gets really interesting. The quantum nature of this superfluid could also explain dark energy. So if the universe is filled with a single dark fluid, how could we ever prove it? The answer, ironically, is to look for the imperfections. We need to find places where the dark fluid theory predicts something slightly different from the standard model of cosmology. Scientists are like cosmic detectives, dusting for fingerprints that the dark fluid might have left behind on the structure of the universe. This hunt requires immense precision. Instruments like the Euclid Space Telescope are currently creating the largest three-dimensional map of the universe ever made. They are charting the positions and shapes of billions of galaxies, looking back through cosmic time. While the idea of a single fluid is beautiful, it comes with its own set of major challenges. The biggest hurdle is a problem of fine-tuning. For the dark fluid to work, it needs to be a master of disguise. It has to act just like dark matter where we see dark matter, and just like dark energy where we see dark energy. The theory has to walk a very fine line. Another significant challenge is explaining the sound waves of the early universe. The standard model of cosmology predicts the pattern of these ripples with breathtaking accuracy. Any new theory, including dark fluid, must match this perfection. So far, most dark fluid models have struggled to reproduce the observed pattern as precisely as the standard model. We find ourselves at a fascinating moment in the history of science, standing at the edge of a cosmic cliffhanger. For decades, our understanding of the universe has been built upon a strange foundation. We have a model that works brilliantly, but it requires two enormous, mysterious ingredients: dark matter and dark energy. These components remain complete enigmas. The quest to understand the dark side of the universe is more than just a scientific problem. It is a fundamentally human adventure. As we move forward, the flood of data from new observatories will be our guide. The solution will likely require cosmology and particle physics closing in on the mystery from different directions. So, the next time you look up at the night sky, remember that what you are seeing is just the tip of the cosmic iceberg. Beyond the familiar constellations and the faint glow of the Milky Way lies a vast, invisible universe waiting to be discovered. We are living in the age of its discovery, a privileged moment in history where the biggest questions about the nature of reality are being actively investigated. The cosmic secret is out there, written in the fabric of space and the motions of the stars. Our journey into the dark has just begun,